So that's the one. Test, 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 test.
Assignments, we don't need to upload anything to Dropbox until next Thursday now, do we?
You don't have to, no, and I'll have it all be in Dropbox 3.
And with the part about gprof apparently being impossible on Mac OS, so if we have a Mac, what do we do about that? Do we just ignore that part of the assignments? And
No, so you're going to do the gprof on SciNet.
oh,
Yes.
I was thinking,
You can't do that. No, this is why we're all switching to SciNet. Okay, so this is working. That's that should be there. No, I don't want that.
It's not an issue. Just message him at work, be like, I know you're busy, but I really need you to run my assignment for class.
Okay, makes sense. All right. Alrighty. Sections. No, just save that. Sure it's all right. Let's get started. Where is it? So, as you may not have noticed, because I emailed you, we're going to extend the deadline for homework 3 to next week and combine it with homework 4, which isn't as bad as it sounds, because it really means we're going to do assignment 3 on the SciNet computer. And we're doing that mainly because we're finding too many incompatibilities between both MobaXterm or Cygwin and Macs with trying to recreate a Linux-like environment. So as you might have noticed on the prerequisites of the course, we said we want you to have a Unix-like environment on your laptop, and that used to work just fine both with MobaXterm or Cygwin and with the Mac, and that just in time things have changed to an extent that some things we can't do. We can still compile, but profiling, especially on the Macs, was an issue. And installing some software on Cygwin is either difficult or very, very slow. So what we'll do is we'll move to SciNet. And for that reason, at the end of the class, I'll do a little mini intro to SciNet. But what this means is that a few of you haven't yet gotten their SciNet account. If you have a supervisor that is an active SciNet user, that means his account is active. He has students that run on our systems. There's really not much of an excuse not to get that for yourself. It doesn't take more than a couple of days, and if time is crunched, we can even expedite that. But it does require your supervisor to give you his CCRI, which is Compute Canada role identifier, which you need to apply to this. So I'll give a link to the exact procedure once more. There's only like a handful of people that still have to do that, but if that doesn't pan out by the beginning of next week, because remember, the only thing you have to do is rerun your stuff on SciNet, let us know and we'll hook you up with a temporary account. But I would urge you to try and do this, because everything that is in the temporary account for the cluster will be gone after the course. And if you're likely to have an account on SciNet at some point in your research, you might as well get it started now. Okay? So the other thing that we had planned for today is to look at object-oriented programming. And we've seen some of this already. Last class, Marcelo, he showed you some examples that are in the standard template library of useful classes. So today, I'm gonna sort of take a step back and explain a bit more basic what these objects and this object-oriented programming is all about, so that rather than just being able to use it in an ad hoc way, you know why these things are the way they are. And hopefully, if you read back the slides of lecture 7, you go, oh, now it makes a lot more sense. So this is a regrouping lecture to some extent. So let's first think about modular programming, which we've done and advocated because it's an extension of this, object-oriented programming is. So modular programming really is done because scientific software can be large and complex and subtle. There can be multiple components that are bolted on later or just are interacting. And so it really helps if you sort of enforce boundaries between sections of code that really are meant for one thing. So there could be a module for output. It doesn't have to know about the physics that's going on in your simulation. It has to know how to write things down. Keep that separate. There might be simulating a climate model, and the atmosphere has very different behavior from your Earth or your oceans. So those could be modules. By keeping them separate, you can test them separately. You could run them separately. When there's a problem in your code, it's easier to find where it is. It makes it also easier to reuse that code. So suppose now you're writing a new program, and rather than just having the atmosphere, you also want to know what the effect is of the moon. You just add the moon as a module. It's of course a bit more complex than that, but there's parts that you don't have to worry about. Different parts of the modules don't touch each other. So what you want to do typically in modular design is to keep things, keep one module per purpose. Keep the purpose clear. Don't have it do more than it needs to do. And then think about what's called the interface. How is the rest of the code going to interface with this? That means your functions. What parameters do they take? What do they return? And how do they do that so that they have a clear and simple function? By doing that interface, by thinking about how the functions, what the functions would look like, you keep that interface separate from the implementation. How they do it at some point doesn't matter anymore. Once that's well developed, that's just hidden, and you just worry about calling those functions for those particular modules and tying it all together on a higher level. So that was modular programming, and object-oriented programming is really an extension to that tries to address some of the limits that you do have when you do this kind of structured programming. So when you're doing structured programming, and it kind of leads to modules, you break up a programming task into smaller bits, and you turn them into functions, and those functions are simpler so you can implement them. And that's a really good way to do just one thing. But what if you have to do multiple actions, or you have to do an action again and again in a different context? A part of an algorithm might be replicated. Another thing that is somewhat annoying is that if you have these functions and they all operate on the same data, but this data is, if you think back to our ants on a table, one part is the number of ants, and the other part is the velocities of the ants, and they're two different arrays, and I would have to pass them to each function, right? So data has to be passed to each function. You have to know in what order, even though the data means the same. I might have, and so this sort of leads to unclearness in what the module does. In addition, the code in those functions has to know exactly how the data is structured, which one of the two arrays is the velocity, and which one is the number of ants. And this was a simple case, and so the code in the function has to know about the data, but it has no control over whether the data is really doing what it's doing. And so since we have to do that again and again, we reinvent the wheel. Don't like that. So what we would really like is more of a component-based approach. Here is a table with ants. That's one thing. I shouldn't have to worry about whether the array is the number or the velocity, how I count the number of all of that could be just hidden in the fact that I have a table with ants. That could be my component. And so object-oriented programming is meant to do this one. It takes together the data and the code, and so rather than just having the code, hope that the data makes sense, you have a bit of code that both is in charge of setting up the data in the proper way and acting on that particular data. So this is kind of the model that I have in mind when I'm looking at objects. So here's an object. Imagine there's stuff in the object, and then I have basically sort of interface points. These are functions, okay? But the data is owned by the object, and the functions also belong to this object. So if I have the ants for the table, the ants and the velocities, that's the data in the object, but then there might be a function that is part of that object that says, now move one time step forward. That time step belongs to the same data. So it doesn't have to check that the data is properly or yet another function and yet another. The object is in charge of dealing with the internals. This all is just the driver. So if you think about your driver main function that you were writing for assignment 2, you still had to pass all the data every time. That sort of is hidden when you use objects. That's the point of object-oriented programming. There's a lot of extra stuff to it, but that's the point. Tying together the data and the code that is responsible for the data and can act on the data in a coherent fashion rather than having them split separate. So you can, advantage of that is that you can hide the complexity in the component. You can have a cleaner interface where you don't have to worry about passing in data that lives somewhere else. A clear separation of tasks too. The object is going to be in charge of dealing with the data and acting on it. Your program is just dealing with that as a separate component. Okay. There is a few things that you have to be aware of when you're doing this. Hiding the implementation sounds really nice, and it's great because it makes it easier to develop code. Just be using these things, but at some point when you're doing performance-sensitive work, so your computations have to go as fast as can, you have to know at the very least how much it costs you to use these functions. If I pass it, if I ask the table of ants to be advanced one time step, how long does it take? If I make the table twice as big in each direction, does it take 4 times as long? Does it take 16 times as long? What goes on behind it? You might not have to worry about the implementation, but you have to know if you're not creating bottlenecks there. Another thing that can happen, not if you do it well, but it can happen, is that you could be creating all kinds of temporary objects. And we'll see how that works. And that you want to avoid that. And it's not that hard to avoid. But sometimes these two together, two red dots, mean that at the lowest level of your computation, object-oriented programming in scientific computing is typically not done just for performance. The overhead of having this nice abstraction can kill your performance to such an extent you say, well, I'm only using this for the highest level. So your atmospheric grid and your ocean grid, those are 2 big modules. They could be objects, right? But then each grid point is not going to be an object. So you can't do this too fine grained. You could do it, but it'll just be terribly slow and you won't get your graduate work done. So. Now, in C++, classes start from structs. We saw structs briefly. Structs were handy ways of collecting bits of data. So it's the first step of not having to pass separate arrays and just grouping together. So the syntax was fairly simple. You say struct, you have a name of that struct, you say what you want to be inside that structure. Here's 2 doubles, x and y, and an integer called I. And then I can pass those structs to functions as if they were variables, as if they were types, because they are new types. So A is a structure and it contains an I, which we access by this .I, and it contains an x and it contains a y. I can, instead of passing the whole structure, which would actually make a whole new copy of these 3 elements, I can pass a pointer. That's kind of like passing by reference. So we saw this new syntax of this arrow or a dash greater than, which is obviously meant as an arrow, to access the elements within a pointer of the struct. We'll see the same syntax holds for classes. Now we had a slide. So what is to be seen here right away is that where this makes 1 copy of all 3 parts, so it makes 3 copies. All this does is pass a pointer, which is still in a sense a copy, but it's just one number. So it's cheaper. For this case, that's not going to cost you much. But if there's a lot of stuff going on in your structure, doing it the second way is way, way better than doing it the first way, because you don't have to copy things. It doesn't take time to copy. Now, what's nice about C++ in particular is that you can get rid of the struct keyword. So when you define the struct, point2d itself becomes the name of the type. And then, so that's kind of nice. And another thing we could do in C++ is use these pass by reference things, which is essentially the same as doing a pointer, okay? But now we don't have to distinguish the syntax in the syntax, whether it's a pointer or the actual object. So the functions now look exactly the same, but this is still passed by reference. There's no copy. Again, this is a point I do want to stress. When you're working with classes and structs, you want to try and pass things by reference as much as you can, because it avoids that copy. And because of this syntax, it doesn't change the way your function is started. And then finally, a nice thing to do is to say, hey, these guys aren't changed, A isn't changed. They can protect this, this point2d from being changed by putting a little const in front of it. It has some other benefits, but mainly this is just a sanity check that there's no side effects of this print function to suddenly change your data. So it sort of protects your data. This is the typical way you'll see objects passed to functions, unless there's a really good reason not to. So this is already an object. It's just called a struct. We're going to extend that by allowing not just variables in the struct, but also functions. And functions that are in an object are called methods. The idea is that you don't want to really worry about what is in the object, how it's stored, but just want to be able to use it. Now, you can have different types of objects. So you can have different types of structs. They can be related to one another, and we'll see how we can have a whole sort of family of types in. So the first thing that happens when we're trying to put in functions in an object is we're going to change from using the struct keywords to the class keyword, which is mildly silly, but it sort of stresses that we're working with objects. So the class, just to be clear on what things are called, the class is the type, like how is it structured, and an object is a particular instance of that type. Just as I have the abstract notion of what an integer is a type, I can have several integers. I can have one class of object and then many, many of those objects. Make this. So much as with structs, you define classes that have a class and the class name, and then in curly braces you say what should go in. But you have to be more careful here. You have to distinguish what you want the rest of the code to be able to use from your objects and what the objects use internally themselves. So what goes out, what is public, it goes in the so-called public section. This is the same variable definitions, but here's a function. Remember, a function kind of looked like a variable with arguments, and that's how you would define it. You could also put the definition of it, but in this case, I just put the declaration. So here's an example. I have the same point. The integer is changed name to j. I'm not quite sure what that is. J and x and y is doubles, and then there's this set function, which is supposed to set the values of these variables. That's how it could look. And then that's just a prototype function, right? It hasn't actually set anything. So to set it, I have to define it somewhere. So here's that. Now, if this were a regular function, we just say void sets, just repeat the whole thing. But here we have to indicate that this belongs to the point2d structure or point2d class, and we do that by prepending it with point2d. It kind of works like namespaces, if you remember the namespaces. So this sort of says it's a set function that belongs inside of point2d. So this can go underneath and outside of the function of the original function here. So this is one function. After this, after the curly brace, I can now define these things. That's why I have to link them together again with pointer. And then once you want to use it, if it's just an object, since class name is now a type, I can say class name, object name, just as any variable declaration. I can make new ones with a new, and then I get a pointer back. I can make arrays of them. So much the same as a normal type. But then if I want to access them, I can do, just as with structs, dot and the name of something that lives inside the object. And if it's a function, the same thing works. I just have arguments. So it really looks like a function that just has the name of the variable prepended to it. So for instance, if I have a pointer d my object, I can now set values in that object by putting the name of the object in front of the function. And then since it's set, my object.j should now say that it's a function. Okay? So that's the basic. We've seen how we use these things. We've done this kind of stuff. You might have noticed several of the member functions array. So that was a public section, but if you do things right with object-oriented programming, you're actually going to hide the actual data in what's called a private section. So making it private, we can see what it is, but from the rest of the code, I'm not allowed to use these guys. The only functions that are allowed to use these private variables are the functions, the member functions of the class. So in this case, set. That means that if I want to get out the values of j, x, and y, I have to write a function for them. So that's this get j, get x, and get y. This can get tedious, and it's not always a practical way to do, but it is the object-oriented way to go about things. So, and these get j's and get x and get y become very, very simple. All they return is j, or x, or y. So it's important to note here that these functions not only have access to these private variables, inside these functions I can just call them by their name, by j. This doesn't look like it's defined anywhere. J seems to have seems not to be defined, but it is because it's defined in point to d right over here. So in this way, you sort of implicitly have all of the variables inside your class at your disposal. And what is the advantage of that is that now I don't have to pass each of them in a specific order, so they're all just ready. So just a bit of a warning, and this really only matters if you're trying to do this object-oriented programming in too fine-grained a way. Calling these functions can be, like if you do it a lot, you're going to notice it. You're going to notice that it's slower than just getting j and making j public. So there are cases where you're going to break this stuff. There's cases where there might be one function that really has to get the values of x and y a lot, right? And other functions don't. You can make that function what's called a friend of the object, and now they're allowed to see the private stuff. You want to use that sparingly, but that can be a way to, it's good to know that these things exist. When you find that, now that we will be able to do profiling, your bottleneck is in getting the x and y values. This is where you're gonna break the object-oriented stuff and the hiding a little bit. So is that kind of clear? So we have functions within the struct. These functions have access to all of the variables in that struct. You can make some of the variables private, and so only the member functions can see it. And in that way, I can't accidentally do things with the data that I'm not supposed to. In this way, the object has now become responsible for dealing with this data. And that was the idea of this. The object is responsible for it, not the outside user of the object. Now, to make this really work, we have to do a bit more than just having a struct with member functions. The class has a couple of more responsibilities. So it's more than just a chunk of memory. If you had an array class, and we know an array class, it's called RArray, when you create an RArray and you give it the dimensions, it allocates that memory, right? So somewhere there has to be a bit of code that allocates this memory when you create a class. And likewise, when your program stops or your function stops, that our array ceases to exist, somehow that memory was released. We didn't have to do that. Again, there's a piece of code within the object that does that. And those two pieces of code are called constructor and deconstructor. The constructor is called when you create an object. A destructor is called when you destroy it. And that's where things like memory allocation would be set. Another thing that you can set there is default values. And so we need those two bits and pieces, not for everything. Like for integers, you don't need them. But that's why they're undefined when you define. They don't have a constructor. But for an array, you want to allocate a memory. And so the syntax goes as follows. They're kind of like functions, but since they're implicitly called when you create it or when you delete them, they have a funny syntax where they have no return type. So they look like functions without a return type. And the function is such, or the function name has to match the name of the class. So inside class name, there's a function called class name with no return type. This is the only exception of the rule that functions should have return types. Okay. So this is the piece of code that will be executed when you create this. So whenever you do it this way, class name and object, and then you can give arguments to this that get passed to the constructor, just as we did with our array. We passed a couple of numbers. Or you can do it with new. The same happens. That's when the constructor gets called. So here we can create a constructor for the point2d class. Here it is. It has the same name. You pass it a j, an x, and a y. And then within the constructor, we assign those values to the internal private variables. So those are typically very simple, and I shouldn't be doing more than is absolutely necessary for this object to behave like the object it's supposed to be. Okay? There's more advanced syntactical things you can do in constructors that I won't go over. I'm aware of these, but this is what it's for. So that's what happens when it's created. Now, what when it's destroyed? Now, if this is not allocating any memory, then we don't care too much. It's gone. We don't care. But if it allocated memory or if it opened a file, we want to make sure that when the object is destroyed, that can happen in two ways. But when it's destroyed, it releases the memory, it closes the file, does whatever to release that resource. So this destruction of an object can happen either when an object was created in a function and the function ends, or the object is created in like the body of a loop, like anything between curly braces. When the curly braces end, the object goes away, the destructor will get called. Or you can do it more explicitly with new and delete. So if you create an object, you'll get a pointer back with new. You can delete that object. Again, at that point, it calls the destructor. Now, the destructor is the second example of a function that has no return type. And it has the same name as the class name with a twiddle in front. That's a very funny design decision here. And then we can define it outside of the body if we want to have it do whatever it does. So the twiddle is the destructor, and the name itself, just the name, is a constructor. You can't have arguments to this. It's not so strange, I guess. It's just meant to clean up. There's no options to how to clean up. It's just whatever you did, clean yourself up. So I'm leaving out details, but this is the basic way of what these things do, what these classes and objects do. So you have to know that when you create a class, it calls this constructor, calls the destructor. That's where your memory gets allocated and deallocated if things are done well. Even in the standard template library, vectors, queues, all of these, they take care of their own memory in this sort of a way. They can do some other things, like overloading operators, something you probably want to stay clear of when you're first doing object-oriented programming, but it's good to know that this can happen. All of the usual operators that you can do, like plus, minus, star, by division, modulus, but even equating, parentheses, square brackets, they can all be overloaded. In other words, you can apply them on an object, and the object can have a bit of code in it that says, oh, when you're doing a multiplication, do the following. By default, on classes, these things aren't defined. You can't multiply a point 2D with another point 2D. It's just not defined. The compiler will say this is not defined. But you could define something that maybe does a element by element multiplication or something similar. So you can define these things. It's not going to make it faster. It's going to make your code shorter, but be careful to keep sort of the spirit of these operators in mind, because you could define the plus operator to do a multiplication, and the compiler won't stop. But obviously, nobody's going to use your class correctly, including yourself. So just so you know that this is possible and is used, and that's how vectors can be addressed with square brackets, etc., etc. Right? So that's the basics of just one type of object. And I have objects; they take care of their own data. Some is private, and I can make sure that when they get created, they're proper, and they release whatever memory they use in the structure. A second really handy feature of objects is that you can actually have a whole hierarchy of types. So here's an attempt at such a hierarchy. It's slightly silly, but you can imagine that there might be a type called fruit, objects of the type fruit, of which apple are a particular type, and pear is another particular type. Citrus fruits could be a particular type, and they could have subtypes: orange, grapefruit, lemon. The idea about having such a hierarchy is that I might have a piece of code that works for any fruit. Or I might have a piece of code that only works for apples. Maybe even more specific, grapefruit. So it's possible to have types in a hierarchy such that when I pass an apple to this function that expects a fruit, everything works just fine. Treats it as a fruit, only the things that are fruit-like of the apple will be used. And so you can have both specialized types and generic functions that just use the parts that are common to these types. So this is called inheritance. So you would have to build these types. So you build a type, you say, okay, here's a generic type, and I'm going to make a specific type. So you would first create fruit, and you say, well, from fruit derives apple. It's not a very good way of calling things. You're not deriving it, but that's what people say. Okay? So if you had a base class, this would be your fruit. You make a derived class. This could be your apple. And the syntax is to do a colon behind the class name and then public base class. Anything that was possible with a base class or with your fruit, this derived class can do now too. So if suppose I can squeeze any fruit, there would be a squeeze function here. Then I don't have to redefine that squeeze function in the derived class. It could just use the squeeze function from the base class. An example of a matrix, I won't go into too much detail, but you can imagine you have a generic matrix, elements, fill them. It's kind of a mini R array. And then you could have a specialized version of that. That's a square matrix. And this one's very silly, and it's not very well thought out, but this is the idea. Anywhere where I can use a matrix, I can use a square matrix, because it's a type of matrix. The opposite is not true. If it expects a square matrix, I can't put it in a matrix. It might not fit. So that's the idea. And then if it's specialized, they can do things that only work for, say, a square matrices or whatever work well, like a trace. Example of how you use it. So you use it kind of the same way. The fill routine was just for any matrix. Any matrix can be filled, and the square matrix can therefore be filled because it's a matrix. And then only Q can be traced because it's a matrix. I'm going to skip over polymorphism, just because that is the advanced one, and I should play with it. But there's ways to make sure that your code distinguishes different specializations of your code. That's just the beginning of object-oriented programming. We're really not going to do much of it. Okay, we're going to use them. You've used them already, but we're not going to be asking you to write them. In your homework, you're allowed to use them if you want. They're a good way to enforce even more modularity. I'm definitely not against them. But it is noteworthy that if you're doing high performance computing, so that's this HPC, while it's very elegant and makes writing your code easier, it can amount to quite a bit of overhead. So sometimes you just have to throw that out and say, not at this level. How do you know when that is? Profile. So that's all I want to say about classes and objects. That's more than enough maybe for what we're doing in this class, this course. Any questions? I hope you noticed that we saw quite a bit of this already in previous classes, and we're just going to see. I hope this tied it together a bit better. Then we're going to get ourselves onto SciNet. So about 80% of you already have a SciNet account, but you might not have used it or logged in yet. When we get new users, so SciNet, you weren't quite familiar with it. We run large supercomputers. They're sort of located at U of T, although not really. They're just north of the city. And we operate them as a national service. Any Canadian academic researcher and their students and postdocs and collaborators can use them, and we will help them use these computers. We're going to use them because we want to eventually get to parallel programming. And so we had visions getting everybody accounts towards the end of the class where we do parallel programming. With parallel programming, you want to use many cores at the same time to attack a problem and make it go faster, which is why you want to use a supercomputer rather than your own laptop, where after 2 cores you might be done. To see that power, you need access. We're going to get earlier access just because of the difficulties with compatibilities with Macs and Windows machines to even try to make them look like Linux boxes. So what we're going to use is what we call our GPC supercomputer. By the way, a supercomputer is just a computer that is fast at the time. What was called a supercomputer in, say, the 70s was slower than your cell phone, and maybe even slower than your watch, depending on what you're wearing. So we have fairly fast ones, but the real thing that sets them apart is their size. So we'll go over that a bit. So running on a supercomputer, however, is a little bit different than running on your own machine, and that's why we have to sort of give an intro. We have intros regularly for new users. There's actually a more extensive one next week at 10 a.m. at our offices if you want to sign up and want to know more now. So what I'm covering now is the basics that you'll need to get going with your homework. You can wait for the next intro, like longer intro if you want. This is what you'll need right now. So it's a bit different. That's why we need a little intro to how you use it. But it is a bona fide Linux environment. You'll have G++, Make, Boost, gprof, Valgrind, RA. They'll just be there. And so we can focus on using them and learning that. I would still encourage you to try and install as much as possible to on your own machine, because it's faster and easier just to develop on your own machine. Right? There might be the odd day where SciNet is down, and then you're stuck. You can't do anything. So I would still encourage you to try and get these work, but I don't want you to be held up by it anymore. So here's our GPC. GPC stands for the wonderful prosaic name, General Purpose Cluster. Pride ourselves in our poetry of naming. What is it? Okay, so imagine you had a fairly beefy desktop with 8 cores, and they're running at 253 gigahertz, not hertz, sorry. And then you took those fairly beefy boxes with 16 gigs each, and you put about 4,000 in rows, kind of like this, and you connected them together. You'd end up with over 30,000 cores. We've actually extended a little bit, it's an old slide. And you end up with a machine that is theoretically capable of performing 328 tera floating points per second. I'll have you look up how much that is. Now that's if you used every core and every cycle and every addition and every multiplication to its max. So the truth is you're about 80% at peak at best. But that's its spec. But each of these, but you still mostly deal with these on a box by box, or what we call node by node basis. So each of these nodes has 8 cores and 16 gigabytes. And that's sort of your restriction within that node. And until we do serious parallel programming, you're not going to get off node. It runs a Linux version called CentOS 6, which is a derivative of Red Hat. You're more familiar with that. It's Linux, looks like Linux. It's still the second rank open as in available for academic research Canadian HPC system. We're slated to get some more because internationally we're a little bit behind currently. Somewhere next year they'll be faster and fewer shiny machines. But the fact that we have 30,000 cores here means a lot of science gets done in this. Okay, anything from geophysics to personalized medicine, although not really personalized, but research on it, molecular simulations, climate simulations, all of that runs on this, and just lots of stuff gets done. It dates from 2009, so you will find that your codes run slower on this machine core by core, but towards the end of the course, we'll see how we use all those cores together, and then we'll get to that. So how do we use this machine? Well, it's actually not our only machine. And that's why we sort of have a gateway or a set of gateway machines, and then you go to the actual machine. So the gateways we've called login nodes. So when you log in, you can use a program called SSH. It's likely already there or not. You can get it into Sigma or MobileXterm or on the Mac. It's not that hard. And since you're going to leave this terminal alone, it doesn't matter that things were sort of troublesome before with either of those two. So you SSH in with your username. So you replace username by your actual username at SciNet at login.scinet.utoronto. Don't forget to log in or you'll never get in. And these are gateways. So while you can use them to transfer some data or just get in the door, you're not on the GPC yet. To get on the GPC, you want to get to these blue guys. Those are the development nodes. And we've made a nice little script to get you onto the GPC. It's called GPC. You type in GPC and get on to one of the 8 devel nodes. Recently increased the number of devel nodes. So that gets us from this node to that node, and now we're on the GPC. These are devel nodes. They're shared by many users. This is where you compile your code. Maybe do a short test run. But if you want to do proper profiling or timing, you don't want to be on these nodes because other users are using the CPUs too. And so one time your program runs in 2 seconds. Next time it takes 10 seconds because other users are using stuff. So eventually you want to get to these red guys, compute nodes, which you can get exclusively for yourself, but you have to request them. Hey, while you're developing and editing and compiling and preparing make files and scripts, etc., you're on the blue nodes, you're on the GPC devel nodes. So once you're there, and once you've logged in, you'll see that you have a directory of your own called something like home, SciNet, RSOM. That's mine. PWD, if you're not familiar, that's the present working directory. We've created another directory for you too called Scratch, or $Scratch, which is actually translates to something longer like that, where you have a lot more room. You might you'll need to use Scratch when you're running on one of the red nodes. You can use home when you're running on the blue nodes. Just so that it's easier to find these long directories, they're in environment variables called $home and $scratch. And they have this long structure where G is the group name. So for me, SciNet, the first letter is S, then a group name, and then your username. So depending on what group you will be in, you'll have a different different poem and different scratch, and this is how you get it. So you're in your home directory, you want to get cracking. What do? Well, you'll need some software. You'll need at least some, we want to get our gprof and our g++ and our Valgrind and our, how do we get that? And you'd be sad, look at them because none of them work, not even GCC. And this is because we have hundreds of active users, and they all want a different bit of software. So we can't install software by default. So other than the essentials, like listing your files and CDing and that kind of stuff, nothing is installed where you can see it until you use the module commands. So what the module command does is basically give you access to a directory that has this software installed. And this allows us to do multiple versions. So that's why when you try and ask what modules are available, and you can do that by typing in module avail, you get an enormous list. This is just the top of like hundreds of these modules. That can be annoying. Absolutely, it's a long, long list. There's some way to maneuver through this, but you'll have to load one of these modules before you can use anything. So loading modules is module load. You want to get rid of everything you've loaded in the past, module purge, module unload, you can do a specific one. Avail, we just saw, you see all the available lists, modules. Module list, just list what you've loaded. And then, just to help you out a bit, a module help, with the module name tells you what a module is about. Maybe the module has a name. You go, is this boost or is it not boost? Module help will tell you. Or if you just don't want to look through the whole list yourself, you can do module find and give a keyword or a phrase, and it'll search for a module and tell you, hey, I have a module for you here, or I have 10 of them that have that in their name. You pick. Okay. And so you'll load your modules. You can use shorthand. So you might have noticed most of them have a name, a version, and then there's defaults that have it that will be loaded when you don't specify the version. Again, not the best thing to do. So you can, because they basically the defaults are all old, and that's so best to be specific. You'll need an account to get in. So if you don't have that, here's the link one more time. Basically, your supervisor has to give you an ID number that you can use to ask for your account. If anything of that goes wrong by, say, well, even if you've already found that it doesn't work, email us, figure something out, but most of you should be able to do this. Then you can read the SciNet tutorial. It's actually sent to you when you get your account. There's a GPC Quick Start too. Here's the link. And that'll get you started. At some point, if you're going to be a more heavy user, you want to go to an intro to SciNet. And then another step that is, of course, very important. You already have your code for assignment 3, or if you started with it, you want to copy it over. So this is how you would do that. So from your home machine, you use a little utility called SCP. If you're on Windows and you want to use WinSCP, fine, that will work too. But on the command line, you'd basically say what file you want to copy, and then the syntax is your username at login, and then colon, and then the file. Don't forget this colon, or it'll actually create a file that's called username at login.scinet locally. Colon is important. Again, logging into GPC was like this. Saw that already. The dash Y you need if you want to do any kind of graphics or open Emacs in a separate window or something. The dash Y, but other than that, that's not that. Then some modules you could load. Just some suggestions, but things that will help you get going. GCC, I would recommend version 4.8.1 just because most of the modules are compatible with that one and it's recent enough for the homework. Then you can compile with G++. And then there's Intel compilers that we have too for this course. Don't worry about it. But if you're going to do production stuff, you probably want to try your stuff out with the Intel compilers too. Different topic again. Other useful modules, we've got Boost. Here it is, but it's under CXX libraries. We have RRA, also under CXX libraries. Newer versions of GDB, Valgrind. And then there's this funny OpenMPI module. It turns out that Boost depends on this module. It's a module for doing parallel programming. Boost has some capabilities of doing parallel programming. We haven't gotten there yet, but to be able to load Boost, you'll need this library. So if you don't load this MPI library, in particular this one, Boost will not successfully load. Yes, there is a default Boost. That's true. This one is just a newer version. And that default one doesn't have, for instance, these MPI capabilities. So if you ever get there, so if it worked now, fine. If something broke because you're using a newer syntax, post this every time. So what I would suggest to do, if you're even a little bit familiar with scripting, put this thing in a file and source that file. If you don't want to do it every time. But yes, you have to do it every time. So once we're done developing, we will have to run. We want to do our profiling on a clean red node. Remember our red nodes? The compute nodes, we call them. And you get one of those compute nodes by asking the scheduler, which makes sure that these nodes are shared fairly between all the users, for a node. Now we have a little shorthand of getting one for a short time, for 2 hours, called debug job. So you just type in debug job from any of the GPC devel nodes. It'll ask the scheduler for a node. It'll hang there for a little while until it's found a node. Typically does not take long. If you all start doing it at the same time, it might take long, but it takes about a minute for the scheduler to find your node and see which one's free. And then you have your prompt for 2 hours. You should be able to do homework in 2 hours. As I said, you can do tests on the devel node, but your profiling and your timing should be done. So get you a dedicated node. Nobody else is on the node. You've got 8 cores and 16 gigs at your disposal. Okay, go to town. The job script we will get to when we do real parallel programming later. But because you're on a brand new node, you'll load all your modules again. Okay. So at some point, figure out scripting a little bit to write a little script to do your load. Kind of talked about the homework already, so get your SciNet accounts, push your supervisor. Does it work? Let me know, because I can give you a temporary one, so at least you can get your homework done. But eventually you'll want these things in. Read the tutorial, the quick start, finish your assignment 3 on the GPC. gprof is there, it works. Even Valgrind, if you've not tested it out yet, try that. And then this is the new due date. With the same late policy, a week later from this, half a point per day after this, that kind of stuff. Yeah? I still want you to try it out. Okay, so copy it over, run it there, and give me the gprof on that one, and just to check that everything works out, because this is also going to be your entry into SciNet.
So if I've already written,
yeah, absolutely. Yeah. There is no limit, but there's a limit to the number of debug jobs that can be there simultaneously. So don't make it hard on your fellow students and do like 2 debug jobs. The debug jobs are interactive, right? So you're not going to, unless you can type with both hands separate commands at the same time, which is, I say, good for you. Just have one terminal with the debug job.
once the job stops,
Yes, yes. Yeah. All right. See you guys next week. You'll probably have to go outside. There are people not there.
Submit the homework today. We can submit it next.
Yeah.
Okay. Thank you.
Quick question. When we compile on the developer node, do we just bring the executable onto the compute node? Or
The fun part is that they can see, the compute nodes can see your share your home directory with the devel nodes.
Okay.
So everything is already there.
Okay. So we can just move the executable.
You don't even have to move it.
Oh, okay.